The purpose of this math interlude is to review Fourier series, which I believe pretty much all of you have seen already. So this will be a fairly rapid review, although I will add at the end a connection with linear algebra and quantum mechanics that you might find useful, although that's all extra credit, not something that you have to know for this course, really. More as a service for future use. Now, as you know, Fourier series is about writing periodic functions on convenient forms. So let's say that f of t is a piecewise continuous periodic function with period tau. And that means that we can write that f of t equals f of t plus tau at all times. So this is what a periodic function looks like. It essentially repeats itself with some interval tau, as you know. So as long as it's reasonably well behaved, and by that I mean that, first of all, it has to be piecewise continuous, and there are a few other conditions you have to place on it. I'm not going to get into that because that's mathematical corner cases that don't really concern us in physics. Then we have that we can write f of t is mostly very close to being equal to in most cases. In other words, we can write this function as a superposition of cosine functions and sine functions. And omega here is the angular frequency. That's just 2 pi over tau. We can also write it in a couple of different forms, as you may be aware. Here's another choice. Which is now you have an amplitude and a phase. And we have yet a third form that we can write this on, which you should have seen as well. We can sum n from minus infinity to infinity and write it like this. And that's the most compact form that we can write the Fourier series on, although it comes at the cost of the Cn coefficients here being complex numbers. As you also know, we can find the a's and the b's, and by extension also the d's and the n's, by doing the following, or using the following relationships we can show. But I'm not going to do it here. And this also, all these apply if n and m are integers. Now, this math actually gets a little simpler if we work with the complex, or the exponential representation of the Fourier series. It turns out that this one integral identity is equivalent to all of these. All right, so if we have that, we can actually find the coefficients. We can find the a's and the b's here, just by making the following, by noting the following. And if we take the integral, and then we can see that this integral, according to this result, has to be 0. And that this integral, well, that's given by this result here. So assuming that m is not equal to 0, let's do that just to make things a little bit simpler, then this becomes equal to am times tau over 2. So we then have, in order to find the a's and the b's, the following. Like that. We can also write, if we like, and just to put it all together, I'm going to copy this. So this is true as long as f of t is periodic with period tau and is sufficiently well behaved. And by that I mostly mean that these integrals actually have to exist. So this is Fourier series. You should already be quite familiar with it. But just to refresh your memory, I'm going to do one example with one function and calculate a and b for the case of a square wave. So regardless of whether this makes sense to you or not, if I plot it like this, it should be quite clear what it actually looks like. So it's equal to b for half the period, and then minus b for the second half of the period, and then that repeats. So the next thing we're going to do now is, in order to write this on a Fourier representation, is that we're going to calculate the cosine and sine coefficients in the Fourier series using these formulas here. I should mention that I'm integrating here from 0 to tau. You might have integrated before from minus tau half to plus tau half. That's the same thing, really, because as long as you're integrating over a full period, the result of this periodic function, which is periodic in tau, both the sine function here and f of t is periodic in tau, you will get the same result. Okay. So we can make life a little bit simpler for us, though, by seeing that, well, this is actually an odd function. Since it's an odd function, only those part of the Fourier series here that are odd will contribute. That is, not the cosine part. So we can say that f of t is odd, and that means that all the a sub i's are 0. So the only thing we have to calculate are the b's. And we do this as follows. And if you wonder what I'm doing here, I'm actually taking two integrals and solving them as one, because the integral over this part is exactly the same as the integral over that part, except that they're separated by a minus sign. So that makes things a little bit simpler. And here I just use the fact, of course, that omega equals 2 pi over tau. That's equal to 1 always, and so is that. This, however, varies. The cosine of n pi varies depending on the sign of n. So one way to write that is actually as minus 1 to the power of n. So that way, if n is odd, then that's minus 1. Just like cosine of 1 times pi. Cosine of pi is minus 1. And if it's even, then you get cosine of 2 pi. For instance, if n is 2, then you get cosine of 2 pi, which is 1. So that's an interesting replacement you can make. And this means that I can then write another way you can write this, if you don't want to write a sum that goes only over odd functions, is that you can actually rewrite this in the following way. Like that. Okay, so I've now prepared a little Mathematica program that essentially plots this function depending on how far you sum. So it doesn't sum all the way up to infinity, but from 1 or from 0 up to 30 for the for this particular function here, the square wave function, and for a few others. So let's take a look at that briefly. That's what it looks like. Unfortunately, I can't show the solution at the same time, but you hopefully remember what it looked like. So what this does, it plots the function that we're interested in, and it plots the Fourier series, but it cuts off at some different n. So if you cut off at n equals 0, then the only term you get is the average value. You only get b0 being non-zero in here, and that means that you have a straight line at the exact average of this function. So you can see here, this is a square wave, we have a triangular wave, and we have a few other fun things that I just came up with. So cyclogon is what you get when you take a polygon and put a pen on one corner and then let it rotate along the x-axis like this, and this is for an equilateral triangle. And you can see here the green line is just the average of the function, because we cut off at n equals 1. But if we add in the first order function here, we have n equals 1. Now this is an odd function. We get a sinusoidal. You know, there were no even functions here, so if I go to n equals 2, then nothing changes, right? It's not until I get the next odd one that anything changes. And we can keep adding functions like this, cosines, and we get closer and closer to the initial function. Now, one thing that you can see here is that we get near this discontinuities, we get a lot of this ringing, rapid oscillations. That happens when you have sudden discontinuities, but in most functions you won't have that. So for instance, if you look at a triangular wave and you start adding in Fourier series component, you'll see there's much less of that. And by the time you get to, well, already by n equals 10, it's pretty good, and at n equals 30, you can't really tell the function and the Fourier series apart. This function still, though, has these discontinuities in the derivative. So if you pick a function that doesn't have that, like this one, you'll see that the convergence is even more rapid. Already by n equals 5, you have very good convergence here. You can go all the way to 30, but you can hardly tell the difference. This is the Clausen function, which I picked more or less at random. And you can see here that we have very good convergence, you know, by n equals 15 or so. N equals 30, no difference. This function has some sharp peaks on it, so you have to really go all the way to 30 before you get good convergence down here at the corners. But you can see, as you already know, that Fourier series is a nice way of writing any arbitrary periodic function as a sum of sines and cosines, and that will help us when we're dealing with damped-driven oscillators, where we have an arbitrary periodic function driving the oscillator. Before that, though, in the next video, I will briefly connect what we've seen here, the Fourier series, to quantum mechanics. This is all, as I said, extra credit, but kind of an interesting thing anyway, I think.